It's June 15th, 2016 at about 2:12 Universal Coordinated Time or 10:12 Eastern Time. On your screen is a live view of the Falcon 9 launch vehicle beneath a sparkling sapphire sky at Space Launch Complex 40 in Cape Canaveral, Florida. Welcome to the live SpaceX webcast. I'm Michael Hammersley, Materials Engineer for our Avionics Department. I'm standing outside of Mission Control at our headquarters in Hawthorne, California, and launch is about 15 minutes from now at 2:29 Universal Coordinated Time or 10:29 Eastern Time. We're launching two satellites today. These are the all-electric Eutelsat 117 West B and the ABS 2A satellites. And we're taking them on a geostationary transfer orbit, and they're going to move themselves a little bit higher in altitude to a geostationary orbit. Eutelsat 117 West B will be near South America, and ABS 2A will be near South Asia. We're also hoping to recover the first stage again on this mission, landing it on a drone ship. And we're excited. Let's get started.
Good morning from Los Angeles. I'm Kate Tice, Process Improvement Engineer here at SpaceX. And like Michael said, today we are launching for Eutelsat and ABS. So we're going to be talking in a lot of detail about what those payloads are. So I'm going to be filling you in a little bit about what's going on at our launch site. So this is Space Launch Complex 40 in Cape Canaveral, Florida. You may hear us refer to it as SLC or Slick 40 during our webcast. There's a lot that goes on here that you can't really see, one of them being the hold-down clamps here at the bottom of the rocket. This is also where the 9 Merlin engines are located. For those of you that may be tuning in for the first time to our webcast, that's where the fire comes out. Here we have the first stage as well as the interstage. The first stage is what holds our propellants. So we use liquid oxygen, which we may refer to as LOX, as well as liquid kerosene, also known as RP1. Those tanks are here in the first stage. The interstage is what protects the nozzle of the second stage engine, which is right up here. During stage separation, the interstage and the first stage will come back and hopefully land on our drone ship, which is currently located a couple hundred miles off the coast of Florida. And that is, of course, I Still Love You. So those will be coming back down. We'll have more information on that later on as well. Second stage engine and the second stage will be taking the two satellites out to geostationary transfer orbits, and we do that again later on in the webcast. We'll be giving you more details about that. Now, some of the other things that we often get asked about, these towers here, those are lightning towers. Orlando, Cape Canaveral is the lightning capital of the United States, and so we want to make sure that our vehicle is protected from that high amount of energy that may come down. So what is very difficult to see is we've got some wires here connecting those towers as well, and they kind of encapsulate a little bit around the top just to protect that vehicle from all sides. So that's a little bit about what goes on at Cape Canaveral.
Good morning. Thank you to those who have got up early on this Pacific coast to watch the lovely launch of Eutelsat and ABS to Geostationary Transfer Orbit. My name is Brian, and I'm one of the automation software engineers here in Hawthorne, California. And today, I want to provide you an overview with two aspects. Number one, the general phasing that most SpaceX launches go through, and then number two, the specific mission for today. So in terms of the general things that we do on launch day, as you just saw on the pad, and as Kate just described, Falcon 9 is essentially two rockets stacked on top of each other. Both of those first lift off from the ground from the propulsion from first stage. At a certain altitude, they separate. First stage then goes back to land, like at the drone ship today, or at the landing zone in other missions, and then second stage continues on to deliver the payload to its desired orbit. That is the primary mission for every single time you see one of these webcasts. It's to get the payload that is sitting within the fairing at the tip of second stage to its intended orbit. Now, what is that specific mission for today? It's to launch a satellite from Eutelsat and ABS, as my co-hosts have mentioned. Now, Eutelsat's model is 117WB. Now, that really stands for the longitude that it's going to, 117 degrees west longitude. This is to provide coverage to the Latin Americas. Remember, geostationary satellites stay above the same regions as Earth rotates. This is Eutelsat 117WB because we launched Eutelsat 117A just 15 months ago. Now, ABS is the other satellite within the fairing. This is 2A, and it will be going to 76 degrees east to provide coverage to portions of Asia and Africa. It's called 2A because we launched ABS-2 15 months ago on the same flight. As with all programs, we'll bring you live footage of liftoff as well as another attempted landing of the first stage so that we can get that reuse nailed down.
Hello, I'm John Innsbrucker, Falcon 9 Principal Integration Engineer. As I've done in the past, I'll be bringing you status updates and webcast commentary throughout the flight from our launch desk here in SpaceX headquarters in Hawthorne, California. Now, as you heard, it's early morning here in Hawthorne, but as you also saw at the start of the webcast, the day shift employees are gathering for the Falcon 9 launch. They're standing in front of our Mission Control Center where they'll be watching the flight along with all of us here on the webcast. Now, currently, we're deep into the launch out of sequence at T-minus 11.5 minutes before launch. This is where the ground computers, assisted with the Falcon 9 flight computers, are doing the final checks of the vehicle and loading propellants. So let's take a look where we are right now in the countdown. Now, the Falcon 9 rolled out to the launch pad at about T-minus 17 hours yesterday. We got out to the pad in plenty of time to allow the spacecraft teams to do spacecraft checkouts. We went vertical, we went through our testing early this morning, and we are currently now loading propellant onto the first and second stage. Now currently fuel is already loaded onto the second stage. That is the RP1 kerosene fuel. And we have just ended loading fuel onto the Falcon 9 first stage. So now we're just down to loading the liquid oxygen onto both the first and the second stages. That's going to continue up until just about the T-minus 2 minute mark. Now on the spacecraft side, the Eutelsat and the ABS teams, once we got vertical on the pad, they did their checkouts. They've gone from external power to internal power and just verified that they're on internal. All their systems are looking good. The range is ready to support with the tracking and flight safety systems that we need to fly into space today. And the weather's looking good. You can see the blue skies with just some puffy clouds in the background. The upper altitude winds are still looking good. So everything is cooperating right now for a launch in just over 10 minutes.
Eutelsat is one of the world's leading satellite operators. They currently have 40 geostationary satellites in their fleet, and Eutelsat 117 West B will be the second next-generation satellite in their Eutelsat Americas fleet. It'll be co-located with Eutelsat 117 West A off the west coast of South America, and this new multi-satellite neighborhood will strengthen the video capacities at that longitude. It will be offering key services to Latin American clients in telecommunications and government services, and it's expected to enter commercial service in the first quarter of 2017. Now, these video services are going to include direct-to-home services, as well as support for digital terrestrial television networks. The satellite has 48 transponders with 4 regional beams covering Mexico, the Caribbean, most of Latin America, and even the tip of Antarctica. It's operating in the KU band, which is reserved exclusively for satellites. Satellites, if you will recall, communicate with electromagnetic waves, which includes light and radio waves. The KU band is a portion of that spectrum at 12 to 18 gigahertz, part of the microwave spectrum. And I know you're wondering, your home microwave oven operates at 2.45 gigahertz. Another cool fact is that the hosted payload from Raytheon, it will be hosting a payload from Raytheon that the Federal Aviation Administration, will be using for aviation safety. ABS is one of the world's fastest growing global satellite operators, and they have 6 satellites serving 80% of the world's population. ABS-2A will be co-located with ABS-2 at 75 degrees east near India and Pakistan, serving Africa and the Middle East, Russia, South Asia, and Southeast Asia. It's also equipped with high-performance KU-band beams. It's part of the same spectrum as the Eutelsat satellite. And this satellite will be offering ABS's customers expansion capacity as well as in-orbit redundancy for growing direct-to-home business. Both satellites are designed for direct-to-home services. The map that you see at the moment is not the satellite's coverage as much as ABS's world coverage. And they're going to be designed for other VSAT operators. VSAT stands for Very Small Aperture Terminal. That means you can point a small satellite dish about the size of a pizza box at the satellite and gain access to the communications network the satellite operator provides. And this footage that you're seeing on the screen at the moment is of the 2 satellites undergoing final preparations for launch. After this step, they get integrated into the fairing, and they are currently standing upright at the launch complex. Man, those solar panels are enormous. Up next, we've got some cool footage of our Texas site, where the rocket undergoes its own preparations.
Hello, my name is David Heffley. I'm the site director for the SpaceX Texas Rocket Development Test Facility here in McGregor, Texas. What makes McGregor unique is this is generally where the fun happens, in my opinion, so we get to see some really cool stuff in McGregor, Texas. We get to make the smoke and fire. So last year we averaged about 400 Merlin tests, so that's more than one every calendar day for just the Merlin engine. If you throw the stages into the mix and everything else we do, we could, on any given day, we could be running somewhere in the neighborhood of 6 to 50 tests. SpaceX Texas is about 4,200 acres total. I guess an interesting note on that is about half of it is cultivated that we inherited as we leased the land. So we actually have corn, wheat, and just hay in production on the site as well. We have about 15 test areas. So we're standing in the central hangar, which is where we do the first and second stage integration work. So after we test these stages, we put them in the hangar and we do post-test checkouts before we send them to the launch site. The small site is where a lot of the smoke and fire happens. That's where the engines are tested, the Merlin engines, and second stage is tested over there as well. We also have a component stand over there that does a lot of Falcon 9 component tests. If you go up to the north side of the site, that's where the large site is. So that's where booster stand is. That's where we test first stage. To the west, we have Dragon site, so that's where we test Draco, and that's actually where we process Dragon. So we do all the Dragon cargo offload in Texas. What's also great about Texas in particular is there's always something exciting happening at some particular test stand. There's new boundaries we're pushing, there's new hardware here. We seem to always be in new ground, which definitely means that it's never boring around here. There's always something exciting going on.
We're at T-minus 5 minutes and 22 seconds and counting. Things are looking go for an on-time launch. We're continuing to quickly step through the automated sequence that I talked about. We're bleeding in and chilling the Merlin engines right now. The ground systems are continuing to load liquid oxygen onto both the first and second stages. We polled the team at T-minus 38 minutes for readiness to enter the launch auto sequence, as it's called. That's the scripted sequence where the ground and the flight computers prepare the Falcon 9 for flight. There's minimal involvement by the launch team. That's why you don't hear a whole lot on the countdown nets during the webcast. Now currently in propellant load, we're still putting liquid oxygen onto both the first stage and the second stage. As I said before, that'll wrap up at T-minus 2 minutes. We wait as long as we can to keep the liquid oxygen as cold as possible. That gives us maximum performance for the Falcon 9 to carry our customers into space. Some of the events you're going to see coming up very shortly. We're pressurizing the first and second stages. That'll open up the clamp arms and we'll begin retracting the strongback. So at about 3.5 minutes, you'll see the strongback recline. That'll move to the 77-degree position. That's our launch position. Prop load will finish at T-minus 2 minutes. Over 1.1 million pounds propellant will be on board the rocket. Currently, Eutelsat and ABS teams are ready. The range is ready to support. Weather conditions look good. So at T-minus 3 minutes and 50 seconds and counting, all is go.
Rapid reusability. You've heard this buzzword be used multiple times as a prerequisite for the quest to make humanity multiplanetary. Now, what exactly is reusability? Well, it's comprised of two main pieces, recovery and then reflight. Now, recovery is something that you've seen on our previous webcast we've had some success with. The stage goes to orbit and it comes back and it lands in a safe manner that we can recover it. The second half of that puzzle is reflight. It's making sure that you are ready to fly that same recovered vehicle again. Until you can refly it, it's not technically reusable. Now, we're adding maturity to that recertification program as we speak. But the ultimate finish line for all these rockets is to land. If it lands on the drone ship, it gets taken on the surface of the drone ship all the way to port. That's what you see on your screen now, in the vertical position. It then gets loaded horizontally onto a truck and taken back to the launch site to be reflown. The exact same thing happens if it lands in a landing zone. It gets put on a truck, as you see, and gets taken to the launch site again. The goal is to return to the launch site, get refueled, retested, and then go back up to space. Now, the refueling is a pretty easy part, but the retesting is hard. We want to make sure that the engines, if you remember seeing behind me, they weren't jostled in flight. Nothing was subjected to extreme heat conditions that would cause it to deform in a certain way. That's where automation is key. We need to be able to ensure that the vehicle flies the second time just as safely and just as nominally as the first time. Now, remember, that is a secondary mission. So as we turn our sights back over to the primary mission, before we refly, we must land, and before we land, we must launch. So let's listen into terminal countdown now.
T-minus 2 minutes.
Stage 2 lock secured for flight. Initializing locks, ground closeout. Vehicles in self-line. Stage 1, Stage 2 cryo-helium secured for flight.
VC, verify Falcon 9 is in startup.
Falcon 9 is in startup. Flight software has control of the vehicle. Stage 1, Stage 2 present for flight.
T-minus 30 seconds. T-minus 20.
Falcon 9 secured flight pressures.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the Falcon 9. Falcon 9 has cleared the towers. Team moved to section 10.59 to secure the pad.
Stage 1 propulsion is nominal.
Plus 1 minute into flight. Falcon 9 is heading downrange after lifting off from Space Launch Complex 40 at Cape Canaveral. Currently, the Merlin 1B engines are operating at full power. We're watching the launch from the SpaceX cameras on the ground at Cape Canaveral. Right now, this Falcon 9 is heading through the supersonic phase. It's a little hazy to see on the webcast as we head out into space. We've gone supersonic. You've also heard the call out, MVAC chill has begun. Just like we do with the first stage engines, we are now chilling in the turbo pump on the upper stage engine to get it ready for ignition. Coming up just before T plus 3 minutes. Currently the team is reporting Falcon 9 is operating nominally. Major event coming up in about 30 seconds is shutdown of the 9 Merlin engines. Let's listen in for the call out of main engine cutoff. Shutdown, successful stage separation, and the view from the first stage looking at the second stage. The upper stage engine has ignited. We're on our way into the parking orbit. Let's go down to the floor and talk with the team.
With successful separation of the first and second stage, we now continue on as those two separate stages perform their separate responsibilities. You were just looking at a view of first stage pointed back down towards the Earth. Second stage is continuing on, and we've just had confirmation that the fairings, the encapsulation at the tip of second stage, which holds the satellites, has successfully separated, an important milestone.
Breaking the fairing away like that allows the NVAC second stage engine to perform a little more robustly. It's efficiently, right. It's putting more of that force into accelerating the satellite. The fairing is essentially dead weight once it gets out of the atmosphere. It's very important before that point.
Exactly. So the less weight we can have around the payload and on the second stage, the more efficient the vehicle itself will be, and allowing us to use less fuel in order to get it out to the specific place that we're trying to drive these two satellites to.
Right. A lot of people don't realize we don't need the fairing anymore. Once we're out in space, the fairing is there to design both protection and aerodynamics of the satellite. When we're going through the atmosphere, that needs to be able to push through air very, very cleanly. Without any air anymore, when we're out in space, we don't need that fairing, and so we let go of it.
And while the second stage is continuing to speed up to get into low Earth orbit as the beginning of that geostationary transfer orbit, the first stage is headed back towards the drone ship in the Atlantic Ocean. And you saw a cool shot of the grid fins popped out there. And the grid fins are what's controlling it back through the atmosphere in order to get it to approach the drone ship successfully. There we go. You can see them right there.
And those conjoined triangles of success that you see inside of the grid fins are actually just like small airplane wings. They're used to fly the first stage back to the destination of the drone ship that it wants to reach.
Yeah, so the grid fins are actually one of the mechanisms that I support in my day job on the manufacturing of those. And the reason why we can't really show them to you in person is because they're really big, right? They're made out of aluminum. And we use about, well, let's see, I'll step in front. So they're about this wide and they're about that long. So they're pretty heavy, they're pretty strong, and they're a lot bigger than what you might anticipate just based on the views that you get from the side of the rocket.
Interestingly, they're most useful at hypersonic and at lower velocity speeds. The shape of that sort of crosshatch pattern is such that the shocks that develop from just airflow mean that most of the air around the speed of sound at those sorts of speeds flows around the grid fin, so you actually aren't as efficient in steering the vehicle around the speed of sound. But very high above the speed of sound, you're getting good control, and close to sort of lower in the atmosphere when you're moving slowly, you also have that good control again.
And so we're going to transition into the phase where we do the re-entry burn. You'll see these grid fins deploy like little T-Rex arms in a few seconds after the re-entry burn once we're within the atmosphere.
Plus 6 minutes and 31 seconds. Everything's looking good as Falcon 9 heads to space. Currently on the trajectory plot, we're headed, as usual, right down the middle of the road between the predicted upper and lower limits projected on the map. We're listening. We've just heard the call out for entry burn startup. This is a 3-burn maneuver that brings the first stage, slows it down to get it ready to come back through the atmosphere. Now, previous flights, we've done a boost back burn. If we were coming back to the Cape, we don't do a boost back burn in this case. We're doing the entry burn. We're waiting to hear the shutdown. And we've got the shutdown. And we'll then listen and wait for the first stage to come back. Meanwhile, the second stage continues to perform nominally as we head into orbit. You can see the glow of the nozzle on the MVAC-D engine. That's our niobium alloy nozzle. That red glow that you see right there on the close-up camera, that indicates temperatures are nominal, a word we like to use here at SpaceX. So at T plus 7 minutes and 42 seconds, everything is go.
Okay, so like John I said, the first stage and the inner stage are coming back down. We're waiting for the re-entry burn to begin any moment now. This is the burn that slows the vehicle down enough so that it doesn't burn up upon re-entry, because given that this is a GTO mission, like we've said before, this is a rocket that's coming back in really hot and really fast.
Yeah, most mission profiles, we typically have 3 burns. It's boost back, then re-entry, then the landing burn. This one, we don't have a huge lofty perspective. We're going much more flat, so it's just re-entry and landing. We're coming into the landing burn now, and you should be able to see it on your screen.
If footage cuts out, we find that the drone ship shakes a lot with that final few seconds as the force from the engines comes down. The landing burn has begun.
You can see the drone ship shaking.
Looks like our feed may have froze a little bit. Again, intense vibrations from the drone ship due to the rocket landing.
Smoke.
Smoke clearing.
Smoke.
I see a vehicle.
I see somewhat of a rocket. Move, smoke. Fingers crossed.
We don't know.
You're seeing what we're seeing right now.
now.
We should be able to have some conclusive evidence in a second once we reestablish video.
You can hear as the footage is coming in and out how everyone's excited.
We're unsure of the status of the landing.
So we'll provide updates when we know if that first stage landed or not. Once the smoke clears and we have confirmation, we'll be able to say yes, it successfully landed, or no, we simply got more experimental data. So we'll return with that in a moment, but now focus back on the primary mission, which is second stage in orbit.
So the animation that you were just seeing on your screen is a good orbit, we're hearing, is what that animation is showing. You can see where the second stage is in relation to the Earth and how it's continuing. You're hearing the crowd react to that jumping footage of the first stage on the drone ship.
We don't know yet, just like you guys don't either. But again, the focus is the second stage, and it continues on in low Earth orbit to take us to that geostationary transfer orbit.
Unfortunately, there's no Wi-Fi out in the middle of the ocean yet, so we are unable to get that clear picture as we had hoped. This is unfortunately a result of the circumstances that we have, but we will be sure to update you on that as soon as possible.
And we'll stay on for a second just in case we hear of any conclusion on the first stage. But the sequence of events as we continue on, we'll go through the coast period. That's what we're entering now for second stage. There's no burn happening. We are coasting to a specific spot to get to that point in, I believe it's at apogee, where we burn, no, it's at perigee, where we burn again, so that we can reach us to the final highest apogee of 360,000 kilometers or so.
36,000 kilometers.
36,000.
Okay, so with that, like we said before, we're unsure of the status of the first stage, as well as everyone else, as you can hear behind us at the moment, but we'll be sure to update you when we can. We're going to go into a break for just a moment while we enter the coast phase. We will return as we get closer to the second stage startup, as well as the double payload deployments, so be sure to stick with us.
Welcome back. We're at T plus 24 minutes and 52 seconds. We're just beginning to reacquire telemetry from the Falcon 9 as we're beginning to prepare for lighting the upper stage engine. I'll bring you commentary as we go through that. Currently, we are pulsing the settling thrusters on the upper stage. That's helping keep propellant at the back so that it covers the inlets to the turbo pump. We've chilled in the upper stage engine's turbo pump. We're about, I think, 30 seconds out from ignition. Now we'll stay in a preparation phase right up until it's time to spin the turbine. We use onboard high-pressure helium gas. We can't carry a long pipeline from the Earth. It's not like we're operating off an electric cord all the way back to the launch site. We carry our gas and propellants on board. We'll spin the turbine pump, and that'll start the burn sequence. Waiting right now to see the start of the burn that'll transfer us from parking orbit into the geostationary transfer orbit. And we see ignition. Burn is underway. The burn will last just under 1 minute. Tank pressure is looking good. Chamber pressure is looking good. You see the characteristic red glow on the niobium alloy nozzle extension. Now currently, to keep the payloads underneath the maximum acceleration, we throttle the upper stage engine. We're beginning to do that right now to stay underneath the roughly 5G acceleration limit for the Eutelsat and the ABS spacecraft. You can see on the webcast we're continuing to burn. Chamber pressure is continuing to look good. And we're into the shutdown phase. And we have engine shutdown. We'll give a minute here, let the stage settle out. I'll go take a look at the orbit and see how we are.
Okay, so just a quick update on the status of Falcon 9 on the drone ship of course I Still Love You. Unfortunately, it appears as though we lost the vehicle. We don't have a lot of details of this just yet, but the important thing to keep in mind is that we did receive a lot of really good data from this. As always, these are experimental attempts, and although we can say that Falcon 9 was lost in this attempt, we did get a lot of really valuable data from it.
And with the second stage engine cutoff, now the second stage is in the geostationary transfer orbit. We've just gotten confirmation that it is, in fact, a good geostationary transfer orbit. So what that means is that the satellite, or the second stage and the two satellites, were starting in low Earth orbit, and if that were to continue, it would be quite close to the Earth. The geostationary transfer orbit turns it from a tight circle around the Earth to a big egg shape. And what the satellites are going to do when they eventually get to the top of that orbit is circularize it so that they end up being in that geostationary orbit.
Exactly, and with the conclusion, as John mentioned, of the second stage burns, this concludes the SpaceX launch portion of the entire trajectory today, and we transition over to kind of the mission phase. So the two remaining upcoming events are the separation of Eutelsat and ABS. Once deployed, they'll continue on with their mission. Now, regarding the configuration of those two satellites, remember they're sitting inside of the fairing at the top of the second stage. The fairing has been deployed, so now they're exposed to space. The configuration is that ABS is on the bottom, mated directly to the top of second stage, and then Eutelsat is sitting on top of ABS.
So there are clamp bands that connect the two satellites together, as well as ABS to the mechanical interface between ABS and the top of the second stage. That clamp band will be released, and there are springs that sit underneath that will sort of push the satellites away from the second stage, and that constitutes the payload deploy, after which then that takes care of most of the mission phase, and just sort of confirm that those satellites are in a good position to move themselves up to the geostationary orbit.
Now, of course, we don't want to be jolting the satellites in any way, so this push that we're talking about is a very gentle motion. It's more of a release. It's not really just like chucking it out into space.
Exactly, and so we're going to come up on our first deployment here in a second. Eutelsat, because it's on top, is going to be deployed first. So it's going to be pushed off, and then about 5 minutes later, ABS will be deployed. Now, once they're deployed, they use their onboard ion thruster systems to do some pretty cool stuff.
Yeah, so ionic propulsion is something that's really interesting. It's very different from the typical fire explosive kind of propulsion that you see like with Falcon 9, for example. Ionic propulsion is different because we basically take xenon particles and they get fired through a chamber.
The satellite. We're not launching the satellite. Yeah. This is the ABS satellite.
Exactly.
And the
this is the propulsion systems aboard both of these satellites. And essentially, we take xenon gas and we fire those. The satellites are firing those particles through a chamber, and we should be coming up on satellite deploy in any minute, any second here.
Provide you live video. The Eutelsat deploy is when we're going over ground station coverage on the cusp of a few different ground stations. So if we don't have perfect video, that is the reason. But Eutelsat was confirmed to be deployed successfully.
So we'll bring you visualization of that as soon as we can, but like Brian said, the video feed is a little tricky at this point. So back to ionic propulsion. So we're basically taking xenon particles, we're firing electrons at those atoms, and by doing so, they become positively charged. This makes them an ion, hence the name ionic propulsion. These ionized particles, atoms, are then going through what is a magnetic grate, essentially. So because they're positively charged, they're going through a grate that one has a negative side, one is a positive side. They get acceleration from that. They basically bust out the back, and that is what provides force to the engine itself. So the acceleration for this type of propulsion is on the slower side. In fact, the amount of force that is given off by this type of propulsion is about the same force that a piece of paper gives on your hand as you hold it. So it's really good for propulsion out in space where you don't have friction, you don't have a whole lot of gravity pulling against the payload itself. So this is a good form of propulsion for these particular satellites.
It's also extremely mass efficient, and because mass is so critical on a satellite, you can afford to launch more communication services, which is really the whole premise of what the satellite's doing, if you have a more mass-efficient propulsion system like the Ion system is.
Exactly.
So after a few moments of a health check on Eutelsat, it will begin to fire up and start using that propulsion system to slowly get itself to its final geostationary orbit. ABS will do the same after deployments in a few moments.
So Kate, you'd mentioned that the final release is quite soft. There are a lot of environments for the satellites during the actual ascent phases that can be fairly strong. And if you're curious to see exactly what those environments are, we have a payload user's guide that we share with our customers when we're doing launches to make sure that the satellite and the rocket are compatible in terms of the environments that are getting transferred from the one to the other. That payload user's guide is at spacex.com/Falcon9 if you are curious to see some of those nitty-gritty details. It includes things like the power requirements prior to launch, like how we're actually keeping the satellite powered up before it switches over to its own internal power. It also includes the shock loads from the large mechanical events that are occurring during ascent, including all the engine starts, the engine shutoffs, the separation events, max Q. Each of those sends a quick pulse of energy through the vehicle, some of which, if it were to get transferred too strongly to the satellite, could potentially damage it. We make sure that that does not occur by communicating those specific requirements to and from our customers.
So just a quick recap in case if you're just joining us, we had a great ascent of Falcon 9 and a great stage separation. First stage and the inner stage returned back to, of course, I Still Love You, our drone ship off the coast of Florida. Unfortunately, we lost the vehicle in that landing. However, second stage, as you can see, is performing nominally. We had a confirmation of good separation of Eutelsat, and right now we're just waiting on the second deployment for ABS.
Speaking of some of that device sensitivity that you're mentioning that we have to satisfy requirements for, these satellites have all sorts of suites of sensors on board to perform different duties that need to be safe throughout the launch process. Some of those include star trackers, sun sensors, GPS positioners, things that tell the vehicle where it is, how it's positioned, so that it knows how to get to its final destination and knows what orientation to be in when it does exert some thrust from that ion at the back. And so those sensors and those suites need to stay safe throughout the launch process so that they can be used right now as they are to get us to our final position.
And in particular, they need to also stay clean. Staying clean is a big part of staying safe. for those sensors. You can imagine if you're trying to look through a telescope and it's just got some smudge on it, you're not going to be able to see what you're looking at. Same thing happens for the satellites. And so inside of the fairing during ascent, we make sure that the satellite environment within the fairing is very carefully controlled. We're actually filling it with dry nitrogen to drop the relative humidity. And we always make sure that we maintain positive pressure within the fairing so as not to pull in uncontrolled atmosphere during ascent. If you have condensation that forms, it can carry bits of smudge that would affect some of these sensors. We're about 15 seconds away from that second satellite deploy event. We'll hopefully have good live footage of that.
Have good ground coverage for this one.
So there you see the second satellite. We got some cheers in the background. There's the visual confirmation.
Oh, what a beautiful shot. That's like a film right there.
That's gorgeous.
It's surreal to see, but that's the ring of the Earth as a satellite is deployed away from it. It's still fantastic to see every time.
I just got chills.
Yeah, thanks.
So it turns out that's most of our stuff done. We need to confirm that the satellites are headed safely to geostationary orbit, but we had a successful launch. We did not have a successful landing, unfortunately. Again, this is all experimental, and we're very excited for the day when it becomes regular, and but we're not quite there yet. And we've had 2 successful payload deploy events. So again, that just about closes it up for SpaceX. And best of luck to ABS and Eutelsat for continuing their ascent to geostationary orbit.
So at this time, we would like to thank our customers, ABS as well and Eutelsat, as well as the range and, of course, the whole SpaceX team, and you guys, the viewers. Be sure to check us out on our website, www.spacex.com. But we also got some other cool stuff going on Facebook, Instagram. I love our Instagram page. It's fantastic. As well as YouTube and Twitter.
On a final note, our hearts go out to all the victims, their families and friends who are suffering from this week's horrific tragedy in Orlando. From all of us at SpaceX, our thoughts and prayers are with you, and to those who are still recovering, we offer our best wishes for a full recovery.